Hello everyone, here Dr. Shah. Here I am going to show you how the intensity of light and emissive power is correlated. So already in the we know that intensity emissive power radiated by the black body in any direction theta is given by directly proportional to the intensity of light in the normal directions theta, which is oriented collector, which is oriented at theta angle, and d omega is what, solid angle, and dA is the emitter area. So see in the line diagram here, all the variables are shown in the figure. Okay, this is our collector and this is our emitter with area dA, and d omega is our solid angle, and theta is the angle at which collector is oriented from normal line. Okay, so below you will find and one applications. This is sun, which is generally considered as a emitter, and the solar plate we are having on the ground, which is our collector. So at certain angles it will receive a maximum emissive power. So this we will try to understand in from the animations. So in the animation, see here, in the animation when you will see, this is our hemisphere. Okay, hemisphere. Normal perpendicular to this plane, x this directions, y along normal, z in this direction. So mainly the radiations from this dA area. dA is our emitter area and emitting light in all the directions. So at what angle our emissive power is maximum? Here DEB is maximum. This we will try to understand. So let's switch to the directions for a better understanding. Here different variables exist. See here. Here polar angle. See here, this is our normal. Normal means this one, normal, and this direction is our z axis. Normal and z axis. Here same normal and z axis. When you are changing the theta, when you are decreasing, see here, decreasing. Now just increase the and goes up to 90 degree. See, parallel. So at 90 degree you will find here from universal formula. Okay. So in cos theta d omega dA, as already seen in the here, dEB is directly proportional to in cos theta. The same is presented over here. So when theta is 90 degree, say here 90 degree, so cos 90 is 0. So 0 watt energy will be, emissive power energy will be or delivered in this direction. Okay, just you make it slow, small value. Okay, when you are reaching to the zero value, means just the ray of light is perpendicular or normal to the normal in directions, then you will find here, you will find the cos 0 is 1, means maximum power, emissive power you will receive. See, currently it is 625 watt. Okay, when you are increasing the theta value, the emissive power is decreasing. See, from the real data value continuously it is decreasing, and up to when you are reaching up to the 90, okay, degree, okay, the emissive power is showing the 0 watt value. Okay, so the same thing we will find here. Okay, now the next is azimuth angle. What is azimuth angle? See here, what is azimuth angle? This is represented on x and z plane. See here, z, this is our x and z. When you are changing the this one, okay, like this, means it assumed angle is this one, like this. So is this assumed angle is affecting the DEV value? No, it is not, because in DEV you will find there is no assumed angle. Okay, so assumed angle when you are changing, okay, so the collector when it is at certain assumed angle, there is no effect on the DEB. Okay, that's why the DEB emissive power energy is not changing. Now solid angle. When you are changing the solid angle, see here, seeing here, what is the relationship between the emissive power and the solid angle here? When you will find what is the relationship between solid angle. See, dB is directly proportional to dW, solid angle. So more is the solid angle, more is the solid angle, more will be the dB. See here. So more is the solid angle, more is the emissive power radiating from the black. E means black. Okay, this black body is emitting power like this. So lesser is the solid angle, lesser is the solid angle, lesser will be the emissive power. Okay, so at 0.001 the emissive power is showing is 1.0239 watt. Okay, so increase the value of solid angle, the emissive power is going on increasing. Okay, the same is for the emitter area. When the area of the emitter here, when the area of the emitter, this area is increasing, so it is when you are increasing the emissive, this one area, emissive power, then what is the maximum dB energy emitting from this emitter? Okay, you can find from here. So lesser is the here, lesser is the daa area, lesser is the deb. So lesser is the deb, lesser is the emissive power. So emissive power is directly proportional to the area, emitting area. More is the emitting area, more is the emissive power emitted by the emitter. Now let's understand collector position. This is our collector position, shape which is given here, yellow. So this is our position. Let's change the position. So x-axis changing like this. So the collected area, how much watt it is collecting energy, 0.0021. Okay. So as you are reaching towards the emitter area, more and more energy it will receive. Farther you will go from the emitter area on x-axis, so lesser energy you will receive. Okay, let's put it over here, point at 1.01 meter. Okay, now let's change the y position. See, y at the just moving up. So as we are moving up, so more and more energy is being collected by the collector. So as we are moving down, okay, so lesser and lesser energy is collected by the collector. Similarly, when you are moving the z axis, the z is along this. So as we are moving z, see how the values being changing. Okay, like this. The same thing you can. Now let's talk understand about the intensity. See, the intensity IN and EB has directly relationship. Here IB, here IB, this one IB and IN has directly relationship. So more is the emissive power emitted by this emitter. Okay, more is the intensity received by the collector. More is the intensity, so more is the intensity, so more is the emissive power. See the value, lesser is the intensity, lesser is the emissive power, like this. Okay. This is represented in hemispherical shape. Okay, so the radiations being emitted by this emitter in all the directions in a space. Okay, so you can in the phase angle, see the phase angle is being, let's put it in direction mode. Phase angle you are changing, see the phase angle here and here, both are changing simultaneously, both are same. Better visual mode. See, now it is, means just it is going like this, 90 degree making 0 degree, this is 0 degree, Okay, maximum emissive power will be radiated by the emitter. Now 90 degree, no, no energy emitted. Let's keep it here somewhere 50 around. Assume the angle you are changing. See, the assume the angle is what? See, the assume the angle is just moving like this. Okay, in 3D like this. So you might have seen in the here, assume the angle is this one, phi. Assume the angle is this one, phi a. Okay, like this it is moving. So assume the angle is moving like this. Okay. Solid angle, no solid angle effect. Okay, on the collector. Okay, solid angle is being, more is the solid angle, more is the emissive power radiated by the emitter. dA area, more is the area, more is the energy. Okay, see the projection area is also being going here. Emissive power, okay, position. I am changing the collector position. See the how the values being changing. Okay, by the collected and how much energy being collected by the collector. Okay, the intensity. See the beam is showing like off mode, means there is no energy being delivered by the emitter. Okay, now increase the intensity. As you are increasing, now it is showing with red one, means glowing, means the light energy is being now in on mode. Okay, see here, when you are changing the intensity power, intensity is being changing. Let's play in auto mode. So this is being shown in the 3D for easy and better understanding. So that's all about the radiation intensity in spatial distribution. Thank you all.